Welcome to Unit 9 of Chemistry 101 at Goodwin College. Unit 9 actually deals with Chapter 6, so we've begun bouncing around a little bit. The next two units will cover Chapter 6 and Chapter 9. So we'll do Chapter 6 this week, Chapter 9 next week. In my opinion, they are a little bit of oddball chapters, which is why they come out of order a little bit. And then once we get done with Chapter 6 and Chapter 9, the rest of the course is substantially different than the first half of the course. The first large chunk of the course, including these two chapters, is very mathematical. The last chunk of the course is still a little bit mathematical, but it's much more biological as well. So here we go with Chapter 6, which deals with gases. We've discussed this very early in the course. I probably mentioned earlier in the course that there are three major types of material things. There's solid matter, there is liquid matter, there are gases. So we're going to spend this unit discussing gases, which is why it's emphasized here in red. We have discussed solids and liquids in the other units. We've also discussed gases a little bit, but this chapter deals exclusively with different types of gases. There actually are other types of matter. There are things that are not solid, liquid, or gas. We're not going to discuss them. We really don't, we as normal people walking around in the real world, we don't tend to see these other types of matter very often. So for the most part, we're accustomed to seeing solid things, liquid things, and gaseous things. So we're going to talk about gases in this unit. So one question that I pose to the students in my on-ground class is, how do you know that the air is made of molecules? I assume that everyone who's listening to this basically thinks that the air in the room that they're sitting in is made of molecules, and yet you can't see it. And this is just a little bit of a thought exercise. How do you actually know that the air is made of molecules if you can't see it? The simple answer, and the way that I do this in the on-ground class, is I will walk up to a student and basically wave a book in front of their face until they can actually feel the air. So just because you can't see something doesn't mean that there's nothing there. There are other senses that you can use to detect molecules, and probably the simplest one is the fact that you can feel the breeze either outside or if someone is waving a book in front of your face. So there at least is some simple evidence for the air being made of molecules, being made of atoms, that type of thing. So your book begins Chapter 6 by talking about something called the kinetic molecular theory of gases. Try not to be too intimidated by this phrase. I actually don't like phrases like this. It's a little bit too fancy, and it's basically hiding a handful of relatively simple ideas. This theory of gases is basically your book's way of trying to explain how people have come to think about how the molecules and atoms in air and in other gases behave. So the fact of the matter is, a few hundred years ago, people didn't really know very much about molecules. People didn't know very much about atoms. And people certainly didn't know very much about air and other types of gases. In particular, they didn't know about it because you couldn't see the atoms and molecules in air. But over the course of the past couple of hundred years, people have come up with reasonably good ideas about how the molecules and atoms in the air behave. And this collection of ideas about how the atoms and molecules in air and in other gases behave has been called the kinetic molecular theory of gases. So some of what I say, as far as these ideas, is not going to be earth-shattering news to you. Some of it might be, and some of it also might be a little bit boring, but the idea is to also give you a sense of what is actually happening to those molecules and atoms in the air, even though we can't see them. So your book has this sort of cartoon. This is supposed to be a container, pretend it's a can that has gas, atoms, and molecules in it. And so these little balls bouncing around are supposed to be atoms and molecules. So the first idea in the kinetic molecular theory of gases is that gases consist of atoms or molecules that move around randomly and with high velocity. So high speed. And so they're trying to show that to you in this cartoon. These atoms or molecules are basically bouncing around inside this container randomly. They don't have any they're not moving around with any purpose. They just sort of bounce around, and whatever they hit, they bounce off of it. The other thing to point out is this other idea. They're actually moving very fast. People have taken careful measurements of molecules moving through air. And just as a piece of trivia, we know that oxygen molecules, O2, actually move around in room temperature air at about 1,400 feet per second, which is pretty fast, right? That's you're covering a quarter of a mile in a second. However, the fact is they're very tiny, they don't weigh very much, so even though they're moving very fast, when they bounce into our faces or other parts of our bodies, they're not going to do much damage at all. So again, this is just to sort of give you a sense of what the atoms and molecules are doing in air. They move around randomly, they move with high velocity. Next idea that's part of this kinetic molecular theory of gases. This idea is basically that the gas molecules usually are not attracted to each other. So what they're saying is, see this green atom over here, if it bounces into another green atom, they're probably not going to stick together. They're just going to bounce off of each other like billiard balls. And the same thing with the orange ones, and if a green one bounces into an orange one, again, they're probably not going to stick together. They're not attracted to each other. Which, again, that may or may not be earth-shattering news to you. Obviously, this rule is not always true. There may be instances where gas molecules are attracted to each other. But in general, the molecules bouncing around in the air in the room that you're sitting in are not attracted to each other. They will bounce off of each other if they happen to bounce into each other. The other one, this again probably should not be earth-shattering news to you, is that there's a lot of empty space between the gas molecules. And so they're showing that in cartoon fashion again in this cartoon, because there is a lot of space between them and there is a lot of more or less nothing in between the atoms and molecules in the gas. And this pretty much explains why we can't see those atoms and molecules. For the most part, the air in the room is empty. However, there are enough atoms and molecules that you can feel them when there's a breeze, but there aren't enough that you can see them. So here's another idea that's part of the kinetic molecular theory of gases, and this one might be a little bit of a piece of new news to you. The average kinetic energy of gas molecules is proportional to the temperature in Kelvin. So this is a little bit of a mouthful. Let me try to explain what it means. We talked about kinetic energy earlier in the course. Kinetic energy is basically the energy that's associated with a piece of matter that is moving. So it's energy associated with the fact that something is moving. So what they're saying is the average energy of gas molecules is proportional to the temperature in Kelvin. Proportional to, in case you're not familiar with this, means that the energy of movement of gas molecules goes up if the temperature goes up, and the energy of gas molecules goes down if the temperature goes down. So again, that when it's explained that way, it might not be earth-shattering news, but that's basically what they're saying. They're saying if the temperature of a gas, let's say the temperature of the air in the room that you're in, goes up, then the molecules move around faster. They have more energy. They have more kinetic energy. And if the temperature of the air in the room that you're in goes down, then the average energy of the gas molecules goes down as well. And the other thing to point out here is they are specifying the units of Kelvin. We talked about Kelvin very early in the course as one unit of measurement of temperature that is not used very often, and I said you would probably never use it in real life, but you might use it later in the course. Well, here, this is the part of the course that is later in the course. We are almost exclusively going to deal with Kelvin in this particular unit. So what they're saying is that the average kinetic energy goes up when you raise the temperature, and it relates to the temperature in Kelvin. And I'll explain what I mean by that in a little bit. Your book uses this term, the kinetic energy of gas molecules, and then they have this, this is a Greek letter called alpha, kinetic energy alpha temperature in Kelvin. This is mathematical shorthand. I don't expect you to know this. This is mathematical shorthand that says the kinetic energy of a gas is proportional to, that's what the alpha means, to the temperature of the gas in Kelvin. So that's just some math notation that your book throws in there. I don't care if you know that or not. If you're interested, obviously you can impress your friends at cocktail parties with the letter alpha. So when we are talking about a gas, usually in these types of chapters where you're talking exclusively about a gas, you usually talk about different features of the gas. So the gas can have different features. And again, if it helps to think about something, some concrete type of thing, you can either think about a balloon or you can think about the air in a room or something like that. And the air that's inside of a balloon has certain features. So as an example, we will often talk about the pressure of a gas. So if you think about a balloon, there's a certain pressure on the gas inside of that balloon. And the pressure of a gas is usually abbreviated with the letter P, capital letter P. And we're going to use that throughout this unit. Another feature of gases that we often talk about is the volume of a gas. So again, if you picture a balloon, if a balloon is filled with a certain amount of gas, that balloon has a certain volume, and that volume is usually abbreviated with a capital letter V. Another feature of gases is that the gases will have a certain temperature. So you can have a very warm balloon and it might have a very high temperature, or you could have a very cold balloon and it would have a lower temperature. When we're talking about the temperature of gases, we usually abbreviate it with the capital letter T. And then finally, the other major feature that we use to describe gases is how much of a gas there is in a certain space. Again, if you think about a balloon that's filled with a certain amount of gas, that gas has a certain number of gas molecules, or a certain number of, if you want, a certain number of moles of gas molecules. And that feature, the amount of gas, is usually abbreviated with the lowercase letter n. And in this case, n stands for usually it stands for number of moles of gas, so that's where N is coming from. On the next slide, I want to talk specifically about pressure and units of pressure on a gas. So as far as gas pressure is concerned, it turns out that there are about 6 billion different types of units to describe gas pressure. Obviously, I'm exaggerating there, but there are many different units for pressure. So just to give you a list of some of the names. Sometimes you can describe the pressure of a gas using a unit called the atmosphere, and the abbreviation for atmosphere is ATM. Now, all I really want you to know is that this is one type of unit to describe how much pressure there is on a particular gas. There's another unit which is often used with barometers and in weather prediction. It's called millimeters of mercury. Again, I think it's too involved to go into explaining why it's called this, but this is just a different unit for describing the pressure of gas. It's millimeters of mercury. Hg, just in case you're not super familiar with it, Hg is the symbol for mercury. It's a little bit weird, and the abbreviation is mm for millimeters and Hg for mercury. It's just a different unit for describing pressure on a gas. There's a unit called torr, which is named after another famous dead chemist named Torricelli, and the abbreviation is just torr again. Let's see, there's a different unit for describing pressure, which is inches of mercury, and the abbreviation obviously is In, and then the symbol for mercury, which is Hg. There are units for pressure of a gas called pounds per square inch, and that's abbreviated PSI. Sometimes if you've filled up the tires on your car, the pressure of the air in the tires for your car are very often described in pounds per square inch. There's a different unit called Pascal. Again, this is just named after another famous dead chemist named Pascal. The abbreviation is PA, and this is again just yet another unit of measurement for describing the pressure of a gas in a container. So all of these are just different units for describing gas pressure. You can interconvert between them. I don't expect you to memorize the interconversion numbers. I will give those to you. If I remember correctly, 1 atmosphere is about 760 millimeters of mercury. I think it's 14.7 pounds per square inch is equal to 1 atmosphere. You can basically interconvert between all of these. And obviously, I haven't committed these to memory, so you shouldn't have to commit them to memory either. However, if I give you the conversion information, you should be able to perform the conversions. And as an example, so I want you to be able to convert between different units of pressure. Here's an example, I think it's from your book. It says 1 atmosphere is equal to 760 millimeters of mercury. If the pressure in a balloon is 2.3 atmospheres, what is the pressure in the balloon in units of millimeters of mercury? And you can pause here and try to work through this problem, and I will show you the answer in a moment. So the way that I would set this up is very similar to the way that I set up many of the problems in this course. I would basically take this piece of information and write that as a ratio. 1 atmosphere for every 760 millimeters of mercury. And then I would say, but we actually don't have 1 atmosphere. We have 2.3 atmospheres, which is what your book or wherever this problem came from is stating. We don't have 1 atmosphere, we have 2.3 of them. So if 1 atmosphere is 760 millimeters of mercury, 2.3 atmospheres is x millimeters of mercury, and we solve for x by cross multiplying and dividing. Cross multiply, we get 1 times x, that's shown here, is equal to 760 times 2.3. And we need to get the x all by itself, so we need to divide both sides by 1 atmosphere. When we divide both sides by 1 atmosphere, we get x is equal to 760 times 2.3 divided by 1 atmosphere. So the atmospheres cancel. This atmosphere in the numerator cancels the atmosphere in the denominator. 760 times 2.3 divided by 1 is 1,748 millimeters of mercury. And again, I don't really care that you're rounding to the correct number of significant digits in this case. I'm much more interested in the fact that you know how to actually do the calculation. So 1 atmosphere is 760 millimeters of mercury. 2.3 atmospheres is roughly 1,748 millimeters of mercury. There are 2 relatively important rules when we do calculations that deal with gases. The first rule is specific to gases. So the rule that I'm about to talk to you about pretty much only deals with gases and not other parts of the course. And that rule is this. Always, always, always convert temperatures to Kelvin when you are doing the calculation. And just in case those 3 always were not enough emphasis, let me say it again. Always convert your temperatures to Kelvin. If you are given a temperature in degrees Celsius or Fahrenheit or anything other than Kelvin and you use it this way in your calculation, you will most likely get the incorrect answer. So if I tell you that the temperature of a gas is 20 degrees Celsius or 100 degrees Fahrenheit, you will need to convert it to Kelvin to do the calculation correctly. So if I told you the temperature of a gas was 20 degrees Celsius, you would have to add 273 and convert it to Kelvin, and then this number would be used in your calculation. So always convert to Kelvin. Second rule is more general. This should generally be true when you're performing calculations. When you are making a calculation, make sure that your units are the same on both sides of the equal sign. What I mean by that is that if you have a calculation where you have 10 liters times 1 atmosphere on the left side of an equation, on the left side of an equal sign, and you have 5 liters times x atmospheres on the right side, you have liters on the left, liters on the right. You have the same unit. You have atmospheres on the left, you have atmospheres on the right. If you have the same types of units on the left and the right, you are probably doing the calculation correctly. If, however, you have something like this, where you have liters on the left side of the equal sign and milliliters on the right side, and you try to do the calculation in this way, you are going to get the incorrect answer. And so what you have to do in a situation like this is you're either going to have to convert 5 milliliters into liters so that the units match the units on the left side, or you're going to have to convert these 10 liters into milliliters so that this number matches the units of this number on the right side. Whatever you do, make sure that all of the units match on both sides of the equal sign. Now this rule should generally be true. It should be true for all types of calculations. The convert to Kelvin rule that I discussed on the previous slide really is only specific to gases. And let's see, what else do I need to say? This pretty much is the last portion of the introduction to this chapter. The rest of this chapter is going to deal with different ways that gases can behave under different conditions. There will be a handful of equations that come with the rest of the chapter, and we're going to deal with that in the next section.